In the previous video, we learned about the various ways that a charged particle loses energy as it passes through matter. In this video, we'll turn our attention to photons. Here's a quick recall on some characteristics of photons. So, as we know it, photons has no rest mass. They have a velocity that is equal to the speed of light when they are in vacuum. That's around 3 times 10 to the power of 8 meters per second. We can calculate their energies in terms of Planck's constant multiplied to the frequency of the photon or electromagnetic wave. And its momentum can be calculated as well in terms of its energy and a constant c. Now, keep in mind as we move through the discussion that the photons we will refer to in this lecture are our X-rays and our gamma rays. Okay, not the non-ionizing radiation that are all here, although they're also photons. So, what happens when photons pass through matter? Will it be the same thing that happens to particles? Well, let's take a look. So as photons pass through matter, various interactions may take place. The photon may be transmitted through the material unaffected. They can be scattered in a different direction from that which the incident photon traveled, or they can be absorbed by the material such that no photons emerge on the other side of that medium. In some interactions, a part of the energy of the photon is transferred to the electrons belonging to the atoms or the molecules in the medium. These electrons, because of their short range compared to photons, will dissipate their energy locally around the sites of the interactions. Such locally absorbed energy becomes the cause of radiation effects or damage. So if a photon enters and leaves the medium with its entire energy intact, or if it merely changes its direction in an interaction, no radiation dose is delivered to the medium, and radiation effects or damage are very minimal. Here are the principal modes of transmission, scattering, and absorption of X-rays and gamma rays when they pass through matter. Thomson scattering, photoelectric effect, Compton scattering, pair production, and some photonuclear reactions. In general, these interactions are regarded as mutually competing processes at all energies. The relative prevalence of any particular type of interaction depends on two major factors: the photon energy, which impinges the material, and the atomic composition of the material or the medium through which the photons pass through. This sequence ranks these different interactions as to their predominance and importance with increasing photon energy. For instance, at very low energies, only number 1 is important. At the energies that are commonly used in industrial and medical applications of radiation, 2, 3, and 4 play the major roles. 5 only happens at very high energies. Let's now take a look at when and how each of these interaction happens. Thomson scattering happens at low energy photon interaction. So we have here an incoming photon with an energy h nu, and then it interacts with an outer orbital electron. So in this interaction, the photon hardly loses energy, but simply changes its direction slightly by a small angle, somewhere here. So the atom then, as a whole, will recoil, acquiring a very small change in momentum, but without absorbing any energy. So the scattering angle is very small, since the recoil imparted to the atom does not produce any excitation or ionization at all. So in other words, the low energy photon is simply re-emitted as an electromagnetic radiation with the same energy as the incident photon without depositing any energy to the atom. So the photon is simply transmitted unaffected through the medium. Now, how about photoelectric effect? How does photoelectric effect happens? So we have here another incident photon with energy h nu, and it interacts with an orbital electron. But this time, instead of the outer electron, it interacts with an inner electron, say this K shell electron here. So the K electron here has a binding energy of, let's call it E sub K. Now, only if this incident photon energy E sub B is greater than the binding energy E sub K of our K electron here, can the electron be separated from this atom. So there's an energy requirement for photoelectric effect to happen. So if this photon has enough energy to eject this K electron, what happens is that this shell here becomes vacant after the electron is ejected. So because this is vacant, another electron somewhere will fill this vacancy up, and along the way, emitting a characteristic X-ray or an Auger electron in that case. So in photoelectric interaction, the entire energy of our incident photon is converted into the energy of the characteristic X-ray or the Auger electrons and into the kinetic energy of the photoelectron that was released. A few things that we need to remember about photoelectric effect. So for this to happen, all the incident photon energy is transferred to the orbital electron, which is then ejected from the atom. Now for that orbital electron to be ejected, the photon energy must be greater than or equal to the binding energy of the electron that is ejected. And so the kinetic energy of the ejected photoelectron is equal to the energy of the incident photon minus the binding energy of the orbital electron. Just like photoelectric effect, Compton scattering also involves the ejection of an electron from the atom. The difference is that in Compton effect, the photon interacts with an outer shell electron instead of an inner shell electron. And only some of the energy of the incident photon is imparted to the electron, which results to a scattered photon that has a lesser energy than that of the incident photon. So there are actually three things here that are produced: an ejected electron, a scattered photon, and our ionized atom. So Compton scattering is a predominant interaction of X-rays and gamma rays in the range of 30 kilo electron volt to about 30 mega electron volt. This is a diagnostic range for soft tissues in medical applications of radiation. So Compton effect again results in the ionization of our atom, a scattered photon, and an ejected electron. And the energy of the incident photon is equal to the sum of the energy of the scattered photon and the kinetic energy of our ejected electron. The next interesting interaction is pair production. It's a beautiful manifestation of Einstein's E equals mc squared equation, or the equivalence of energy and mass. For pair production to occur, the incident photon must have an energy that is equal to or greater than 1.02 mega electron volt. If the incident photon has an energy that's less than this, then pair production will not happen at all. So the incident photon interacts with the nucleus of our atom instead of the electrons surrounding the nucleus. And after this photon interacts with the nucleus of the atom, an electron-positron pair is created. So here we have our incident photon. It interacts with our nucleus, and we have an electron and a positron that was created after the interaction. Now, what happens after this? Where will this electron and this positron go? So just like charged particles, this electron will move on and interact maybe with other nearby atoms, while this positron right here will interact with an electron. And when this positron comes to rest and interacts with an electron, another interesting thing happens. Mass turns to energy and becomes photons, each of which have an energy of about 0.51 mega electron volt. So our positron is annihilated and turns into these two distinct radiations with energy that is equivalent to 0.51 mega electron volt each. As we have mentioned before, photoelectric effect, Compton scattering, and pair production are prevalent in industrial and medical applications of ionizing radiation. So in this chart here, we see the relationship between the photon energy along the x-axis and the probabilities of each of the interactions to occur when our photons will impinge on a material with an atomic number Z on the y-axis. So we see here that at lower energies here, photoelectric effect is dominant. At higher energies, with our material having a lower Z, then pair production becomes dominant as well. As we move up through the atomic number, like let's say 100, and then we'll move further into the photon energy range, we'll see that the Compton effect and the pair production can actually happen simultaneously at some point. So this tells us that these three are competing processes in all of these different ranges of energy of our photon. How about photonuclear reaction? So as we've mentioned also a while ago, photonuclear reactions only happens at very high energies. And it happens when our photon gets absorbed into the nucleus of our atom, and one or more neutrons or photons are emitted after that. In other words, there is a nuclear transformation of our nucleus or our atom. So here are some examples of target atoms and their photonuclear threshold energies. So this is the energy needed in order to induce a photonuclear reaction if we're going to impinge, let's say, carbon here with a photon. So our photon must have about 18.7 mega electron volts in order to produce a reaction that results to a carbon atom. And this carbon-11 right here is not stable, and it has half-life of around 20.5 minutes. So if our incident photon does not reach the required minimum energy to produce a photonuclear reaction, then no transformation of the atom will happen. So it's either the photon will be scattered or absorbed by the medium, causing maybe photoelectric effect, Compton scattering, or pair production in that case. There is a difference in emphasis in our approach to photons and charged particles as they pass through matter. For charged particles, we emphasize their energy loss in their slowing down process until they come to a stop. So accordingly, for these particles, we talk about the stopping power of the medium. For photons, instead of slowing down, quote unquote, we consider them as undergoing a reduction in number or a decrease in intensity of the photon beams. We account for them as being either present and available for interactions or lost in an encounter with matter. Such loss or decrease of the photon intensity in any medium is called attenuation and is governed by the photon attenuation coefficient of the medium through which the photons move through. Let's consider, for instance, a narrow parallel beam of photons here, striking a thin plane slab of an absorbing medium perpendicularly. So we use n naught here as the number of photons impinging into our medium per unit area, and n sub L right here as the number of photons that exit on the other side. Now let's take a look at this very small slab of our medium d sub L. So if n number of photons per unit area are falling on the entrance side of this small slab, we can expect that a lesser number of photons, n minus dn right here per unit area, will emerge on this other side. So the decrease of this intensity is attributed to the photons that interact within the slice and are either absorbed or scattered out of the beam. And this loss is directly proportional to the incident number of our photons, n, and also the thickness of our slab, dl. And so we can rewrite this relationship simply as dn equal to negative mu. Mu would be our proportionality constant for these two, n, and then we have the infinitesimal change in our thickness, dl. The negative sign of mu makes dn a negative number, so indicating a reduction of our number of photons right here. So this mu, the proportionality constant, is already our linear attenuation coefficient. This constant has the dimension of a reciprocal of the length and is characteristic of both the medium and the photon energy. To find the photon flux, n sub L right here, at the exit side of our slab, we can rewrite this equation and integrate it over the thickness L to get this final equation right here. So this tells us that there is an exponential relationship similar to that of decay between the incident intensity, n naught rather, incident intensity of our photon beam and the final intensity that went through the other side of our medium. We can also express the linear attenuation coefficient in terms of mass, like the mass attenuation coefficient here. So rho here is the density of our material, or we can also express it in terms of the atomic number or the atomic attenuation coefficient, and A here stands for the atomic number, and N A sub B is our Avogadro's number. Or we can also express it in terms of electronic attenuation coefficient, or in terms of our electrons. The attenuation coefficients are proportional to the probabilities of occurrence of these various radiation attenuation processes, and we can use this as a measure of the relative roles of these processes in the absorption of gamma ray photons. So when we talk about total attenuation coefficient, we mean the sum of the coefficients that are pertaining to Compton scattering, photoelectric effect, and pair production, because each of these has their own attenuation coefficients as well. Here are some examples of total linear attenuation coefficients for gamma ray photons in various materials. So we see here that lead has the highest total linear attenuation coefficient compared to these other medium right here at this particular energy level. And as we move up through the photon energy, we can see that the total linear attenuation coefficient decreases with the photon energy. But still, comparing these four materials, lead still has the highest total linear attenuation coefficient. For mass attenuation coefficients, we can see also the same pattern. So lead here has the highest compared to the other four materials. And as we can see, as we go higher with the photon energy, we see that the total mass attenuation coefficient of the material also decreases. So where can we use these attenuation coefficients for? Well, we can readily determine the thickness of a material that's needed to reduce the intensity of our incoming photons by half using this attenuation coefficient. So this quantity is known as the half value thickness of our material. And we can derive the half value thickness from the relations between the ratio of our incident and the resulting transmitted intensity of our photons in relation to the thickness of the slab through which they move through. This graph right here shows us the relationship in a linear graph. And here we have the relationship in a semi-logarithmic graph. So HBT, or half value thickness, tells us the thickness of the medium that is required to reduce the intensity of our photons by half. And so manipulating this equation right here in terms of our total coefficient, attenuation coefficient, we can get our HBT as equivalent to around 0.693 divided by the total linear attenuation coefficient, or the total mass attenuation coefficient of our medium. So if we know mu, then we can readily get HBT. Or if we know HBT, then we can readily get mu. There are already a lot of data pertaining to the attenuation coefficients of various materials, and these are available in reference books on radiation and nuclear science. So when you're given a problem about HBT, usually you will also be given some information about the attenuation coefficient of the material that you are dealing with. So you will revisit this equation in a later lecture on shielding calculations. So up next, we'll talk about neutron interactions.